Starting with new topic. So we discussed about transformers, that these transformers are different than traditional artificial neural networks. How are they different? They are different because of their own self-attention mechanism. They're different because they're supporting parallel programming, and they're also maintaining the positional encoding. So when we discuss self-attention, this is where the actual magic happens. This is where the actual calculation, or this is where the actual understanding happens. Whenever we send a message to ChatGPT, acting as a human, acting as a writer, acting as a product manager, acting as a financial analyst, it is able to match your tone. It is able to understand your tone. When we ask ChatGPT or any of these generative models, it is able to understand those tricky questions and answer them. How is it able to do it? It is able to do it because of the self-attention mechanism. At the very beginning of encoder-decoder architecture, we have these self-attention heads or multi-head attention network. So what it does basically is, given a sentence, it is going to understand or capture long-range dependencies between words. It is going to capture the long-range dependencies between words and also understand the context of the sentence, of a given sentence. And when it is performing this thing, when it is performing these things, understanding the long-range dependencies and the context, it is doing parallelly, not one word at a time, but it is doing parallelly. So let's look at this sentence. The teacher taught the student with a book. So when we look at this sentence, we have multiple words here. Some of the words are related to each other, and some of the words are related to each other, that is giving meaning to the sentence. We have long-range dependencies as well. We have important words, that is capturing the context of the sentence as well. So to break it down, for the transformer architecture to work, self-attention mechanism breaks down each words into query and key. Based on these query and key, it is going to calculate the value for us. So when we say query and key, given this sentence, the teacher taught the student with a book, first word in the sentence, the, becomes the query for us. Second word in the sentence, that is teacher, becomes the key for us. Now this query is using these two words, we are going to perform mathematical calculation. That is, we are going to calculate the similarity between these two words. Okay, how similar these two words are, and we are going to get a resulting value. So for each given word is going to act as a query, and that will be used against each and every key, that is each and every word inside the sentence, to calculate a value. This value becomes the importance score. Okay, how important it is, what is the context for the sentence. So in self-attention mechanism, how it is working, we are creating three vectors from each of the input values. These vectors or words that we are passing through, they are going to be used as key and query and key, out of which value is going to be generated for us. Every word in the sentence is going to act as a query. That query will go through each and every key inside the corpus, and we are going to calculate the similarity score. Based on the similarity score, it is going to understand the importance and the context to it. Like, it is going to identify the similar words inside the sentence. It is going to understand the important words inside the sentence as well. So let's look at this sentence here. The cat sat on the mat. So when we look at this sentence, the important words here are cat, sat, mat. So to do it, first we are going to use one word. Let's say we have used the as a query, and then for keys we are going to use each and every word and calculate a similarity score. When we look at the similarity score between the and the, it is highest for the. So here this is telling us that conceptually it is understanding the same word. When it is the same word, it has the highest value and then it has the values for the other words. Similarly, when we look at the most similar words in the sentences like cat and sat. So these two words are giving context to the sentence, cat and sat. So we will see that cat and sat will have a good score, will have a higher score. When we look at the other matrix, cat and sat has a higher score. It also reveals the sentence structure, identifying subject, verb, object relationships. Like this cat, subject, sat, verb, and object, mat. It is going to understand the relationship between these words for us. Now when we look at these things, when we look at sat and mat, when we look at cat and mat, we have a value for it. When we look at sat and mat, we have a value associated to it. These values are telling how important these words are and how are they related to each other. Latter words like the and that are not helping to build the sentence will have a lower score automatically. When we look at the scores here, for all these stop words that we have in the context, automatically it will have a lesser score. So this is how self-attention mechanism is going to capture long-range dependencies as well, and it is also understanding the context to it. That what are the important words in the corpus, what are the related words inside the sentence, and how are they joined together. If there is an action performed in the sentence, what is the message trying to convey? Using this terminology, we are going to train the transformer architecture. So earlier we discussed that artificial neural networks, they are not capable of understanding the context of the sentence. Using this self-attention mechanism here, we are now informing the machine that this is the relationship between the words and this is how important each word is. Second thing, the data is not going to go one by one. All the words that we saw in the previous slide, it is not going to go one by one. Instead, it will parallelly process each and every word for us. That when we look at the sentence, the cat sat on mat, the cat sat on mat, it is going to parallelly process each and every word. That is, it is processing the query key value for this word, this word, this word, this word, all at a time. So this is going to reduce the computation time. This is going to increase the training speed for us. So like discussed, unlike NNNs, neural networks, which process elements sequentially, transformer can calculate attention score for all pairs of elements simultaneously. So everything is going to happen together for us. This enables the advantage of parallel processing, and with modern hardware that we have, it is going to significantly increase the training speed and the inference speed. That is, the understanding of the sentence is going to happen faster, and even the prediction is going to happen faster for us. So inside, so moving to the next topic, transformer architecture. So far we have discussed inside transformer architecture, we have multi-head attention that is working parallelly. We have an encoder and we have a decoder. Now let's look at how is this structure created finally. So when we look at this diagram here on the right hand side, we can see that we have a left hand side stage and we have a right hand side stage. This entire left hand side stage that we have here is the encoder. This entire left hand side that we have here is decoder. So one by one, we are going to understand the encoder and the decoder. So inside encoder, when we look at this, given any sentence, The cat sat on mat. Machine is not going to understand words for us. We have to transform them to numbers for machine to understand. So first, these words are transformed to word embeddings. These words are transformed to word embeddings. That is, these words are transformed to numbers. We have number 1, number 2, number 3, number 4. As discussed in the previous slide, we discussed that these encoder-decoder system has a special mechanism of understanding the start of the sentence or end of the sentence. That is called as positional encoding. So inside encoder system, we have input embedding that we discussed, that input embedding is the text that is translated to numbers. Machine can only process numbers. We all know that. So to do that, we are transforming it to input embedding. Retaining the semantic relationship, retaining the actual meaning behind it, using a embedding model, we are transforming these alphabets or words to numbers. Inside the transformer architecture, we discussed that there is a special mechanism of positional encoding. So when we discuss positional encoding, we are informing this encoder and decoder that either where is the sentence starting or where is the sentence ending. So to do this, we are going to put an absolute value at the beginning of the sentence or at the end of the sentence. With this, we are going to say, with this, the architecture is going to understand where is the sentence ending or where is the sentence ending. Where is the sentence starting or where is the sentence ending here. So when we discuss about transformer architecture, so far we discussed that it is broken down into two pieces. One is an encoder part, another is a decoder part. When we look under the hood for encoder part, we have an input embedding, then we have positional encoding. That either end of sentence or start of statement. Either of this. After performing this embedding and informing machine about the start of the sentence, now we pass it inside the encoding. Now we pass it inside the encoder. So far, outside the architecture, outside the transformer architecture, to prepare the data for the encoder system, we translated the words to machine understandable language, that is numbers. Next, we added this positional encoding. Now the data is passed inside the encoder. First thing it is going to pass through is multi-head attention. The multi-head attention. Using this multi-head attention, we know that now the machine is going to understand the relationships between each and every word. How is this word related to another word? And these multi-head attention, we can be having 1 billion heads, 2 billion head, 3 billion head. These heads are responsible to understand the sentence. If we are asking a tricky question, if we are asking a confusing question, a sarcastic question, understanding the tone of the input, machine is going to understand over here. After the understanding, after extracting the useful information from the sentence, now the data is passed to a normalization layer. So inside normalization layer, when we are calculating these multi-head attention values, the values can be really high. It can be greater than 1, it can be lesser than 0. The values can be in a range of numbers. So to put them in a defined range of number, that is to put them in a normally distributed number range, we pass it through a normalization layer. Two benefits of doing it. One, if there's too much weight on either of these values, those values are going to be normalized. The machine is not going to be biased towards a specific word. Similarly, when we are training a neural network and if the values are really high, it is going to put that inside a normal range. So learning speed is going to increase as well. So we pass the input embedding before putting the data into encoder, we are translating the numbers, we are translating the words to numbers, we are adding positional encoding. Next, we are passing it to multi-head attention, where it is understanding the interpretation, the long-range dependencies. After this, the data is passed through a normalization layer to increase the speed of the training, to remove any bias that we might have inside data. Finally, this is passed inside a feed-forward neural network. The feed-forward neural network that we discussed earlier. So this feed-forward neural network is going to understand and learn the sentence, that how are these important words based on values related and what should be the next word inside the corpus. After the learning happens, it is finally passed to a normalization layer to again scale the values, and this information is passed to decoder's multi-head attention. So inside the encoder, now the machine knows the context of the sentence. What is this sentence about? What are the important words? How are they related to each other? Starting from the first word until the last word. Parallelly, not sequentially but parallelly, the power of transformer, the data is also passed inside decoder. This is where the prediction is going to happen for us. Data is also passed inside decoder, that goes through a similar transformation that we discussed here. This data is going to pass through a similar, the data inside decoder is also going to pass through a similar stage, that it is going to go through a multi-head attention, normalization, and then this information is going to come over here inside the decoder's multi-head attention. Here, the context given by the encoder's multi-head attention is mapped with the decoder's attention for the transformer architecture to understand it better. Now the machine knows what is the sentence or what is the question being asked to it, and comes the job for predicting the next word. So to predict the next word, we are normalizing it because we are sending it to a feed-forward neural network. This feed-forward neural network is going to learn the values that we have given. These learned values, whenever we make use of these neural networks, if we had given, let's say, 3 inputs, neural network is going to increase the dimensions to maybe 5 values, 6 values, 7 values, depending on the output layer for the neural network. So we have increased the dimensions of the input. This increase in dimension of input is also helping machine understand the same sentence in different ways. If a similar sentence is given, if someone tells us something, there are many meanings to it. So to understand the meaning behind it, this feed-forward neural network increases the dimension for it, looks at it from different views, and that passes to a linear transformation layer. This linear transformation layer is going to predict a value for us. Now it is going, let's say we have trained this neural network on Harry Potter books, on all the available Harry Potter books for us. So inside Harry Potter, each and every word, inside that book, each and every word is going to build up the corpus. And the Harry Potter, Voldemort, everything is going to build up the corpus for us. When this linear transformation layer is predicting a value, it is predicting probability for each and every word inside the corpus. And what is going to be the final output? Using this softmax layer here, it is going to pick up the probability of the highest word. It is going to predict the probability of it is going to extract the probability of the highest word, and that word becomes the next word inside the sequence. So it is going to predict one word at a time, one step at a time. By using the information extracted by the encoder and the information extracted by the decoder, using both the information combined, it predicts the probability for each and every word inside the corpus. Now, the word with the highest probability becomes the next word in the sentence. Now, to select the highest probability, there are different techniques. We select either the top 5, we allow it to happen for many words. There are many techniques to take the next word in the sentence here. So we so far discussed encoder, Similar structure for decoder as well. And the amazing thing about this is both of them are working parallelly, not one at a time here. So now moving on to the next topic. So we have so far discussed what is this Gen AI era that we are going through. How is it helping us with our daily task? How is it being used in industry? What is the technology behind this? Now let's discuss about the outcome of this transformer architecture. So the topic, Introduction to Large Language Models.